Hello again. Thank you for tuning into our video series Parallel Programming and Optimization with Intel Xeon Phi coprocessors. In this third episode, we will introduce vector instructions and discuss instructions that are supported on the Intel Xeon Phi coprocessors. Vector instructions in Intel architectures are a class of parallel operations which can apply one instruction to multiple data elements for greater throughput. In Intel Xeon Phi coprocessors, vector registers that contains data for the vector instructions are 512-bit wide. This means that each core can process 16 single-precision data values, 16 32-bit integers, or 8 double-precision data points, or 8 long integers at a time. Compared to scalar operations, this may yield a 16x or 8x performance boost, respectively. As evidence from this, a significant portion of the computational power of Xeon Phi coprocessors comes from the VPUs. Vector instructions in Intel architectures were first introduced in 1997 as the MMX instruction set, or Multimedia Extension Instruction Set for the Pentium CPUs. The initial MMX instruction implementation only had 64-bit registers. Modern Intel Xeon processors based on Ivy Bridge and Haswell architectures support 256-bit wide vector registers in AVX and AVX2 instruction sets. First-generation Xeon Phi coprocessors support 512-bit wide vector registers. The instruction set in Xeon Phi based on Knight's Corner chip is called IMCI, which stands for Initial Many-Core Instructions. It has been announced that the second generation of Xeon Phi based on the Knight's Landing chip will also have 512-bit wide vector registers, but will use a different instruction set called AVX512. To the parallel programmer, the instruction set is important for two reasons. First, the programmer may target a specific vector length in the application code so that the compiler can translate the high-level language code into appropriate vector instructions. The second reason has to do with the code portability. If the programmer wishes to use vector instructions without the help of the compiler, for example using assembly, it is important to understand which architectures will be able to run that code. IMCI instructions are not a superset of AVX or SSE2. Therefore, applications compiled for a Xeon CPU cannot run on the first-generation Xeon Phi and vice versa. However, the second-generation Xeon Phi will be back-compatible with AVX, SSE2, and all early instruction sets. So, an application compiled for the Ivy Bridge or Haswell CPU architecture will run on the Knight's Landing architecture, with only exception of transactional synchronization extension instructions from Haswell's AVX2 set. However, keep in mind that backward compatibility does not mean full utilization. Without recompiling the code with the correct vector instruction set, only a half or a quarter of the vector register capacity of Knight's Landing will be used. Another important fact is that applications for the Knight's Corner architecture, the first generation of Xeon Phi, will not be binary compatible with Knight's Landing, the second generation. This is why throughout this training we promote a portable and future-proof method of programming which relies on the compiler to automatically vectorize the code. With this method, porting an application from CPU to Knight's Corner or Knight's Landing only requires recompilation and does not require rewriting the vector instructions. Even though we will rely on the compiler to implement vector instructions, the programmer must know what kind of instructions can be vectorized. This helps to design code in a way that compiler can effectively vectorize. Here is a high-level overview of the Xeon Phi vector instruction set. All standard arithmetic functions add, subtract, multiply, divide are supported for 512-bit vectors of floating-point numbers in single precision and double precision, and also for integers. Xeon Phi coprocessor also supports for FMA, or fuse multiply add instruction, where two vectors are multiplied then add to the third vector in a single cycle. This is useful for workloads with a lot of multiply then add operations, often used in dense linear algebra. There is also support for common transcendental functions like trigonometric square root and logarithmic functions, to name a few. For memory access, vector instructions support the standard load and store instructions to move data from memory to the vector register or from the register to memory. However, Xeon Phi also supports gather and scatter instructions, which load or store elements in a contiguous vector with a stride in memory. Other supported vector instructions include type conversion, comparison, and bitwise operations. There is also support for certain data manipulation instructions like permute and swizzle. All of the above-mentioned instructions support masked operations. In a masked operation, the instruction is carried out for a full vector register set, but only elements that have non-zero mask associated with it will be written back to memory. For the full list of supported instructions, refer to the Intel Compiler Reference Manual. We'll cover the usage of vector instructions on Xeon Phi in a later video. I will demonstrate practical examples of how to make automatic vectorization happen, how to diagnose it, how to guide the compiler toward better optimization strategies, and how to organize data structures for optimal performance of vector operations. In the next video, we will cover the software necessary to use the Xeon Phi. Thank you for tuning in and hope to see you in the next video.